Now let's look into problems that are related to finite automata and context-free grammars, B and W, where B is a finite automaton and W is a string, such that B is a DFA, W is a string, and B accepts W. So what's this? So this is just the finite automaton acceptance language. So in this case, I can view, I'm given a finite automaton and a string, and I need to decide whether this string can be accepted or not. So this is something that can be done using a finite automaton, but we know that a Turing machine can simulate a finite automaton because the Turing machine has more features, right? So the features of a finite automaton are a small subset of the features in a Turing machine. So the more powerful machine, which is the Turing machine, can simulate a finite automaton. So the solution to this, so this may look silly. You know, the Turing machine for this may look silly. It will just say that simulate this finite automaton using this Turing machine, and if the finite automaton accepts, accept. If it rejects, reject. It will look silly, but we will build more interesting Turing machines for regular languages after we are done with this. So a Turing machine for this, let's call it machine M. So M is going to say simulate B, simulate finite automaton B. Let's call it finite automaton B or DFA B on string W. If B accepts, accept, else reject. So this is trivial. Why? Because a Turing machine is more general than a finite automaton, right? And you are just simulating a less powerful machine. And we know that the deterministic finite automaton will terminate within finite time. Well, a DFA will terminate, but what if I give you an NFA in this case? Is an NFA guaranteed to terminate within finite time? No. Well, if you use the NFA as is, you may do an infinite number of epsilon transitions, but we know that for every NFA there is an equivalent DFA, and we have studied a procedure for converting an NFA to a DFA. So if we replace this, if we make B an NFA instead of a DFA, all what we need to do is convert the NFA into the DFA. And we know that there is an algorithm for this that we have studied. By the way, it's an exponential algorithm. The subset construction is an exponential algorithm, but here we don't care. So step number 1, use the subset construction. Okay, so to convert B into a DFA. Then simulate the DFA, not the DFA, simulate the DFA, which is not B, on string W if the DFA accepts, accept, else rejects. Now, the subset construction is a huge procedure, right? In fact, it's not it's not going to be feasible to try to write a Turing machine, a detailed Turing machine for the subset construction. And we're only using one line here. We're just saying use the subset construction. So we are saying here that we assume that if there is an algorithm that is guaranteed to terminate within finite time for this problem, then there is a Turing machine for this problem. So there is a Turing machine for the subset construction. Now what if I give you, instead of an NFA, what if I give you a regular expression? Will you still be able to determine if that regular expression generates the string or not? So what do you need to do? Well, first you make it an NFA, right? We have studied a procedure for converting a regular expression into an NFA. And what's the name of that procedure? The Thompson, yeah. So if I give you a regular expression, first you convert the regular expression into an NFA, then you convert the NFA into a DFA, and we know that the DFA will process any string in finite time. And then this is an algorithm that's guaranteed to terminate in finite time, and we don't care how much time it takes, as long as it's finite. Okay? Okay, so this is the acceptance. So this is the acceptance problem. Now there is, well, in fact, I'm just going to change the name. So it's not AX, it's ADFA for the DFA. So A for accept. So just it's changing the names only to make it more consistent. The next problem is going to be E, empty DFA, which is this. B is a DFA, and L of B equals phi. Now that was trivial. This is not as trivial. This is more interesting. So here you are given a DFA, and you need to determine if the language for this DFA is phi. Now what would make the language of a DFA phi? How would you check it? If I give you a general DFA, say a state diagram, and the state diagram is a graph, right? So a state diagram for a DFA is a graph. How would you process this graph to determine if the language of that DFA is phi or not? What's that?
No acceptance.
Well, you can have accept states, but the language will still be phi, right? I can give you one. So here's a DFA with accept states. With so this is an accept state, and the language is phi. Why is that? So the language here is phi. You can't reach the accept state. So we'll see that the empty checking if the language of a given NFA, a given DFA is empty is going to be useful in solving a more interesting problem. It's going to be a building block in solving a more interesting problem, which is checking the equivalence of two DFAs. So how can we solve this problem? Give me an algorithm for solving this problem. Yeah.
I just have a question about DFAs, but DFAs can have unreachable states.
Why not? Yeah, it can have. So it doesn't have to be a useful DFA. Being a valid DFA is not necessarily a useful DFA, right? But we will see that checking if the language of a DFA is empty is going to be useful. We'll use it in checking the equivalence of two DFAs as we will see. I hope that we will get. No, I don't think we'll cover it today. Okay, so but let's get this done. How do we check this? Think of it as an algorithmic problem. So you just, it's basic, yeah.
Just find all the reachable states, some traverse only,
Yeah.
start state, and if there's no final states in there, then there's no.
Yeah, exactly. Find all reachable states from the start state. So this is the start state. Find all reachable states, just like we did with the algorithm connectivity, with the graph connectivity problem. Find all the reachable ones. And if one of them, if at least one of the reachable states is an accept state, then it's not, the language is not empty. If none of them is an accept state, the language is empty. So this is, so we describe now M. Mark the start state, and then repeat until no more marking is possible. If you have a transition from x to y, and y and x is marked, mark y. So marking the neighbors, basically. For every transition x, y, if x is marked, mark y, and repeat until no more marking is possible. So find all reachable states, and then scan the states. If at least, or in fact to accept, if no accept state is marked, accept. If no accept state is marked, accept. Why accept? Because in this case, the string belongs to the language, which is the language of DFAs for which the language is empty. If no accept state is marked, accept, else reject.